This is a video about how to hand calculate a factorial ANOVA using the deviation score method. The example that we'll be using comes from a book by Aaron and Aaron called Statistics for Psychology. We're using table 13.12. It's an analysis of variance from fictional data based on a study by Blanchard, Lilly, and Vaughan from 1991. The essential nature of the study is we're trying to look at whether or not responses vary by direction of influence, whether the influences are anti-racist, no influence, or racist, and whether the individual is responding from a public or a private situation. What we're doing with this data is essentially filling in the means for each one of these cells. So we have an anti-racist public cell, we have an anti-racist private cell, and so on. The way that we populate these means is by looking at the actual scores. So the first thing that we do with a factorial ANOVA is that we calculate the means for each cell. So this first cell is the anti-racist public cell, and we have 4 subjects in each one of these fictional cells. So the first subject scored a 25, the second subject scored a 20, the third subject scored a 23, and the last subject scored a 24. So we have a total of, since we have 6 cells, we have a total of 24 subjects in this study. After calculating the mean for each cell, we then go through and calculate all of the different deviations that we need, just like we were doing for a regular ANOVA. The total sums of squares are going to be based on the difference between the observed score and the grand mean. The grand mean is determined, as with the ANOVA, by summing up all of the scores for all 24 people and dividing those sums of scores by the total number of scores. We end up with a grand mean of 20. Okay, so the first thing that we do is we subtract 20 from 25, and we get a deviation for this individual between their score and the grand mean of 5 points. We square that difference. Okay, so we've calculated a deviation between the observed score and the grand mean, and we square that deviation. We do the same thing for every single subject. So in this case, it's 25 minus 20 gives us 5. We square it, gives us 25. 20 minus 20 is 0. We square that and it gives us 0. 23 minus 20 gives us 3. We square it, it gives us 9. 24 minus 20 gives us 4. We square it, it gives us 16. We go down to the next group. We use the same grand mean of 20. 22 minus 20 gives us 2. We square it, and it gives us 4. 19 minus 20 gives us negative 1. We square that, we get 1. 22 minus 20 gives us 2. We square it, it gives us 4. We go down to the non-racist, non-anti-racist, and we say 16 minus 20 gives us 4. We square that, gets 16. We do the same thing with every single subject. Okay, so we calculate their squared deviation for every subject. We're eventually going to sum up all of these squared deviations between the observed scores and the grand mean in order to get the sums of the squared deviations total, sums of squares total. After we figure out the deviations or square deviations between the observed scores and the grand mean, the next thing we do is we look at how much variability there is occurring within the groups. That is, how much variability is there occurring between the observed score and the mean for that cell. Okay, so in this case, the individual scored a 25, the group mean was a 23. So we subtract 23 from 25, and that gives us 2. We square that 2, and that gives us 4 squared units between the individual score and the cell mean for this person. We do it for the next person. 20 minus 23 gives us 3. We square that and it gives us 9. The third person, 23 minus the cell mean of 23 gives us 0. We square that 0 and we get 0. The next one was 24. 24 minus 23 gives us 1. We square 1 and it gives us 1. We do the same thing for each subject in each cell, always subtracting the observed individual score, subtracting the cell mean from each of the individual scores. So in this case, it's going to be 22 minus 21 gives us 1. We square that and it gives us 1. 19 minus 21 gives us negative 2. We square that, it gives us 4. We do that same process for every single one of our scores, always subtracting the relevant cell mean from the observed score in order to get the squared deviation between the observed score and the cell mean. The next thing that we do is we're interested in determining the deviations that are occurring between the row means and the grand mean. Okay, so in this case, the row mean is based on the means of the anti-racist influence for both public and private groups. Okay, so that is going to be everybody in these two groups. Okay, so in that case, we're going to have to get the average for the anti-racist group. To get that average for the anti-racist group, this row, we sum up all of our scores for the anti-racist group in both public and private response formats. So I'm going to add up 25 plus 20 plus 23 plus 24 plus 19 plus 24 plus 21 plus 20, and I'm going to divide that by my total number of observations in the anti-racist influence, and that's going to give me that sum divided by 8, which will give me a mean of 22. That is the mean for the anti-racist influence. So I'm going to use that mean of 22 for this row to help figure out how far away the row mean is from the grand mean. So in this case, the row mean was 22. We subtract the grand mean of 20 from that for each person. So it's going to be 22 minus 20 gives us a 2. We square it, we get a 4. Each person in this cell is contributing that same amount. Okay, so it's going to always be this mean of the row, 22 minus the mean, minus the grand mean. So it's always going to be 2 squared for every single person. And you'll see that that same effect occurs for the private response, because we are still, in this case, using the same row mean and comparing it to the same grand mean. So these people, everybody in the same row, contributes the same amount of squared deviation within this calculation of sums of squares. We do the same process for each row. This row had a mean of 21. So when we go down to the no influence row, we're going to be subtracting 20 from 21 and then squaring that. So it's going to be 21 minus 20 equals 1 squared. Everybody contributes 1 in this row. So everybody here is contributing a 1. Everybody here is contributing a 1, and those are in squared units. Finally, we go over here to the columns, and we do the same thing. The mean for these columns, in this case, the mean for the public column turns out to be 20. We get that 20 by summing up all of the scores that are within that public column. So we add up 25 plus 20 plus 23 plus 24 plus 22 plus 19 plus 22 plus 21 plus 16 plus 19 plus 13 plus 16, and we divide that by 12 because we have a total of 12 scores. When we calculate the average for that, that gives us an average of 20. What we are looking for here is how far the column means vary from the grand mean. In this case, the column mean for the public group is exactly the same as the grand mean. So we're going to see column mean of 20 minus grand mean of 20 gives us 0. So all scores in this column will be 0 because all of these will have the same column mean. They all will have the same grand mean. So in this case, there is no difference in the column means and the grand means for the public response format group. We look over to the private response format group and we see that their column mean also turns out to be 20. Okay, so the grand mean is always going to be 20 in this case, so we're going to say 20 minus 20. So all of the subjects in the private group also contribute 0 sums of squares, zeros along to the variance within here. That leaves the calculation of the interaction effect. The primary reason that we do an analysis, a factorial analysis of variance, is because we're interested in the interaction of our two factors. So in this case, whether it was public versus private and the direction of influence. We believe that the responses vary as some interaction, some special relationship between these two variables. That's why we conduct it as a factorial ANOVA rather than as a simple one-way ANOVA. To calculate these interaction effects, what we do is we take for each individual person their difference between their observed score and their grand mean, their observed score and their cell mean, their row mean and the grand mean, and their column mean and the grand mean. So if we look at the very first person, this person had a 25. The difference between their observed score and the grand mean, right, is 25 minus 20, which gives us 5. That's this 5 right here. We look at the difference between their observed score and the cell mean. 25 minus 23 gives us 2. That's that 2 right there. The row mean minus the grand mean. The row mean in this case was 22. The grand mean was 20. So it's 22 minus 20, which also gives us a difference of 2. And then finally, the column mean minus the grand mean. In this case, both the column mean and the grand mean were 20, so that's 0. You sum up all of these differences and you square that sum. So you do all the subtraction. 5 minus 2 minus 2 minus 0. So this is the total deviation that we're trying to explain. This is the deviation between the observed score and the cell mean. This is the deviation between the row means and the grand mean. This is the deviation between the column means and the grand mean. We subtract all of these other deviations from the total deviation for that individual. So it's 5 minus 2 minus 2 minus 0 gives us a 1. We have one unit that is not explained, okay? We have one unit left over that we haven't explained by differences between the score and the cell mean, by the row average and the grand mean, by the column average and the grand mean. So we have one unit left over. We square that, so we have this individual is contributing one squared unit of interaction that we have not explained. You'll see that every individual within a cell contributes the same amount of interaction. After figuring out all of these contributions to sums of squares, we actually compute the sums of squares. So the total sums of squares that we're looking at, the total amount of variability that we're trying to determine, is based on adding up all of these sums of squares deviations between the observed score and the grand mean. Okay, so in this case, we are going to take 50, which is this sums of squares, plus 18, this sums of squares total, plus 10, this sums of squares total, plus 24, this sums of squares total, plus 82, this sums of squares total, plus this 30. And we sum them all up, and that gives us 214 squared units that we have to try to explain. We do the same thing within. Okay, so this is going to be 14 plus 14 plus 6 plus 20 plus 18 plus 14, which is right here. This is the sums of squares within. This is the sums of the squared deviations that are occurring within cell. Okay, so this is within cell variability. So it's 86 squared units occurring within each cell. The next thing that we're going to be looking at is the sums of squares that are due to the columns. Okay, so this is this one right here. Okay, this is the issue of our column score is going to help us know whether or not we have a difference between the column mean, that is whether it's public or private, and the grand mean. So in this case, the sums of squares for columns for every single cell is 0. So it's going to be 0 plus 0 plus 0 plus 0 plus 0 plus 0 equals 0. That tells us that there is no variability between our columns and our grand mean. Then we compute the sums of squares for rows, and that will involve us looking at the information that's in this column. That is the difference between the rows and the grand mean. So in this case, it is going to be 16 plus 16 plus 4 plus 4 plus 36 plus 36. We sum those up and we get 112. Now, and to get the sums of squares interaction, we just add up all of the interaction squares that we have here, which is going to be 4 plus 4 plus 0 plus 0 plus 4 plus 4. If you don't want to go through the hassle of actually hand calculating all of these interactions, and you're confident in your calculation of the sums of squares total, the sums of squares within, the sums of squares column, and the sums of squares rows, what we know is that if we add up sums of squares within plus sums of squares column plus sums of squares rows, and we subtract that from our sums of squares total, whatever is left has to be the sums of squares of the interactions. Okay, so if we added up 112 plus 86 and we subtracted that from 214, we would get 16, so it would check. After we calculate all of these sums of squares, okay, these are all the sums of squares deviations, we then break it up to see if we can explain it. The total sums of squares that we have here are 214. Our total degrees of freedom will be 23 because we have 24 subjects and we lose 1 degree of freedom total across those 24 subjects. So our remaining areas for degrees of freedom have to sum up to that 23. We get those degrees of freedom here. So in this case, degrees of freedom for columns, we have 2 columns, we lose 1 degree of freedom for columns. So instead of having degrees of freedom of 2, we have degrees of freedom of 1. We have rows, we have 3 rows. We lose 1 degree of freedom for the rows, so that's 3 minus 1, which gives us 2. The interaction term is just the product of the degrees of freedom for rows and the degrees of freedom for columns. Okay, so we're going to multiply 2 times 1, we're going to get 2. Within cell is going to be total degrees of freedom minus the degrees of freedom associated with everything else. Or we can take our total sample size, which was 24, and we end up subtracting each cell from that. So we had 6 cells, 24 subjects, so it's 24 minus 6 gives us 18. The remainder of it, in terms of calculating population variance estimates, is the same way that we did it when we did the one-way ANOVA. The within cell variance here is going to be our denominator for every F value that we calculate. So the first thing that we'll calculate is the population variance that is occurring within cells. We take our sums of squares within cell of 86, we divide it by 18, which is our degrees of freedom, and we get 4.8. That is our population variance estimate in squared units within cells. We can then go and look at columns, so it's going to be 0 divided by 1, which gives us 0. 112 divided by 2 gives us 56 squared units of population variance estimate between the row means and the grand means. And then we have the interaction term, which is going to be, in this case, we have sums of squares 16, which we had calculated up here. We divide it by the degrees of freedom for interaction, which is 2. So we have 16 divided by 2 gives us 8. To calculate these F values, we simply divide the population variance that we are wanting to explain by the within cells variance. This is what is not explained. This is what is explained. So in terms of columns, we get 0 divided by 4.8, which gives us 0. For the rows, we have 56 divided by 4.8, which gives us a pretty robust F value of 11.7. For the interaction term, we divide 8 by 4.8, and that gives us an F value of 1.7. We compare these F values that have been calculated to our critical F value, and we find that the only effect that we reject in terms of the null hypothesis of no difference in means between groups is for the rows.